Hey guys, Nick here, and today we're going to take a look at a quick review of scientific notation and some basic rules regarding exponents, how you multiply two numbers with exponents, because this will come up quite a lot in physics problems because you might deal with very large or very small numbers, and your professors might even give you the information to the problem in scientific notation. Now before we get started, just as always, if you want to help us out, if you like the channel, if you like the style of explanation, the biggest favor you could do us is to drop it in your class group chat, help other people out. It would be great for the channel to help it spread. Alright, without further ado, let's start off here with just a quick review of some exponent multiplication, exponent division, and rules about negative exponents. So the concept of an exponent is that you will be multiplying whatever number appears here, the base, by itself a certain number of times. And this number upstairs, the exponent, tells you how many times you should multiply the base by itself. So actually, so we can be really clear, we're going to do 3 to the 4th. That way you know which is 3 and which is 4. So 3 to the 4th means multiply the base 3 by itself a total of 4 times. So there's 4 self-multiplications of 3. Now, the rule for what to do with adding exponents, which you might have learned before, 3 to the 4th times 3 squared, you might have learned that you can add the exponents together to get an expression for this without actually having to expand it out. And that's true. This does end up equaling 3 to the 6th. Now, just as an intuitive, why does this happen? It's because over here, you have 3 multiplied by itself 4 times. And then over here, you have it multiplied by itself an additional 2 times. So there's 4 multiplications by 3 here, and another 2 multiplications here for a total of 6 multiplications of 3 by itself. So that's really why the rule of adding exponents works. Oops. Now, similarly, if you're dealing with dividing exponents, let's say we have 3 to the 4th divided by 3 squared, the typical rule that you were probably told is you subtract the exponents. And again, it kind of makes sense if you write these out why that is the rule that makes sense. So in the numerator, you'd have 4 multiplications of 3 by itself. And in the denominator, you'd have 2 multiplications of 3. So 2 of the 3's that originally were in the numerator getting multiplied are canceled out by the 2 factors of 3 in the denominator. And what you're left over with is the 2 upstairs that haven't been canceled out. So basically the effect of this 2 was to kill off 2 of the 4 upstairs. So subtracting exponents as usual would give you the same answer of the answer would equal 3 to the 2. Okay, another quick rule that we can go over is how you deal with negative exponents. So negative exponents aren't really that intuitive in the same way that, let's say, fractions are much less intuitive than, let's say, having multiple of something. However, it does make sense if you look at all the rules why a negative exponent is defined to be the thing that it is. So just the general rule for a negative exponent is if you see a negative exponent, it means that this is the same thing as 1 over the quantity, but with a positive exponent instead. So instead of 3 to the negative 2, that's the exact same thing as 1 over 3 to the 2 power. Okay? So I will often refer to this as bringing a number upstairs or downstairs. Now, a reason why this might work, or this might seem intuitive to you, again, you don't really have to remember this too much, but it's good to just have a knowledge that somewhere out there this has been safely and intuitively defined. The intuition might be if you have 3 to the negative 2 and you multiply it by 3 cubed, the result had better work if you choose to do it the add the exponents way, so it should give you 3 to the first power, or just 3. That's the adding exponents way, and the bringing stuff downstairs way would be 3 cubed and bringing this 3 to the negative 2 downstairs to become 3 to the 2. This is 3 factors of 3 divided by 2 factors of 3, or if you prefer, you can do 3 minus 2 because you're dividing the numbers and get the answer of 3 to the first in the same way. So basically, this tells us that the definition of bringing stuff downstairs of the negative exponent is the one that works the way it should. And it allows us to use our add the exponents, subtract the exponents rules without really having to think about it too much. Okay, perfect. Now, just something to note, guys, these rules only work because both of the bases that you're multiplying together are the same. So, for instance, if you had something like 3 squared times 4 to the 5th, you aren't allowed to just add the exponents, and it wouldn't even really be clear if 3 or 4 should appear as the answer. And you certainly can't make this 12 to the 7th. Remember, you have to just consider it as repeated multiplication, and in this case there would be no real shortcut. You'd have to just multiply all the numbers out and you'd get a really large number on your calculator. Okay, something real quick I want to do that isn't really exponents, but I want to remind you of the distributive property. It's something that you'll use just a hair with scientific notation. It doesn't pop up too often. Multiplication is definitely what you want to know. However, it is useful to know how to do, and it appears on tests sometimes, so I'll give it to you. So just a quick review of the distributive property. And again, we'll use this later, only for a tiny bit, but it could be on a test, so I'll go over it. The distributive property says that if you have a number outside of parentheses, and 2 numbers are being added inside of the parentheses, the correct thing to do to quote-unquote bring the 3 inside the parentheses or distribute the 3 over the parentheses is you multiply the 3 by each thing inside. Oops, sorry. So the correct thing to do would be to write this as 3 times 4 plus 3 times 5. Again, you're bringing the 3 and multiplying it not just by the first number or the second number, but you're going to have it multiply each of the numbers that were inside. So one 3 attaches itself to the 4, and another 3 attaches itself to the 5. And if you were to plug these into the calculator, these two expressions, you'd get the same number. That's how the distributive property works. Now, what's important, and what I want to remind you of here, or actually point out to you, you might not have noticed it before, is the importance of going in reverse. So we did this problem in a forwards manner where we distributed the 3 into the parentheses. But just as equally, you can sort of extract the 3 if you see it appearing on top of 2 terms. So just as equally, we could yank the 3 off of both of these guys, so kind of take this 3 and this 3, oops, don't want to erase, and bring them both outside and reinstate the parentheses. right? Again, you see the 3 in both things. Your mind tells you, oh, I can factor that out. This is called factoring. Okay, so both the forward, called distributing, and the reverse, called factoring, will pop up throughout physics. Factoring is, you probably are already used to distributing, but factoring isn't really that easy to understand or easy to, I suppose it isn't really that easy to pick up on when you should factor. So as we go through the course, I'll point out when there's factoring, and I'll be really careful to let you know that it's there and how you should maybe guess you want to factor. Very often what will happen is your teacher will ask for something, let's say a variable v to be expressed by itself, and you might have 3v plus 4v equals another variable, maybe t. Again, don't worry about this if it's confusing to you. This is just a taste of where you'll see it later. And if you want an expression like v equals something, you could, of course, add 3 and 4 first, but if it's a more complicated problem, it might be good to know that you can yank the v outside. Then you can clearly tell that this is 7. And then later divide both sides by 7. So that, again, this is just a taste of where you might see it later in the course. So we'll be on the lookout for this later in the course, but don't worry about this for now. When you're plugging numbers in, this won't be nearly as important as when you're asked for an answer in terms of a bunch of variables, which tend to be very difficult. I had a lot of trouble learning how to do those. Okay, so now we're going to move on to the meat of this, which is scientific notation. Now, scientific notation is useful so you don't have to write out an enormous number of zeros, or if you're dealing with a really small number, you don't have to write 0.00000, so you don't have a lot of decimal places. For example, a useful thing might be distance to the sun is this long. And as you might imagine, that's only the distance to the sun. The distance to the edge of the universe will have many more zeros. So it's really convenient to be able to write this as something like this instead. So basically, scientific notation allows us to not have to write as many zeros, and instead group the number of zeros, or alternatively where the decimal point should be put, and you just fill in the zeros. You kind of lump that into this extra piece here, 10 to some power, and then the actual number, whether it's 1, 1.5, or 2, that appears with all those zeros attached to it in some way, comes out front. Okay, now a more palatable example that you might have a better handle on is a smaller number, where you know what 10 to the, let's say, third power looks like, whereas 10 to the 11 is kind of hard to keep track of. So learning this by example, let's take 2940, and let's see why writing it as 2.94 times 10 to the third, let's see why writing that is the correct way to write that in scientific notation. Now again, what we've done is the decimal point used to be here. Now I didn't tell you how we got this number, but I'm going to show you that this is the correct way to write that number. The decimal point used to be here, but we said, it's too far over to the right. There's a lot of digits. Here there's only 3, but up in the previous example there were 8 zeros. So here we don't really need to do it, but we can for practice. So we'd like to, instead of having the decimal all the way to the end after a lot of digits, we want to instead have a number where the decimal point is very close to the front, and then have the number of places we need to move the decimal point be stored in the 10. So if we actually write out what this is, it's 2.94 times 10 cubed is 1,000. And if you put this into your calculator, or if you remember that when you multiply a number by 10, you basically move the decimal place over 1 to the right. Multiplying by 1,000, which is 10 3 times, we're going to move the decimal place over 1, 2, 3 times. So the result is 2940. Okay. So basically, when we were going from the scientific notation here back to the standard form here, we were cashing in the powers of 10. We were multiplying them back into the number and moving the decimal point. Versus if you want to go in reverse, you're storing the decimal point's location in these powers of 10 that come after the number. Another example that you might have seen before has to deal with negative powers of 10. So this would correspond to numbers that are smaller than 1, where you need to divide by 10 a bunch to get the proper small number. So one example would be the number 3.4 times 10 to the negative third. Now again, if you want to write this out, this is, remembering our exponent rules, 10 to the negative third upstairs is the same as 10 to the positive third downstairs, which is 1,000. And now again, whenever you divide a number by 10, you're moving the decimal place over by 1. Just as a reminder, for example, if you take 3 divided by 10, you take 3 and you move the decimal place over 1 to get 0.3. So here, we're dividing by 10 3 times. 1,000 is 10 to the third power. So the instruction is to move the decimal place in the other direction relative to the last example 3 times. So the first factor of 10 gets you to 0.3. The next factor of 10 is 0.034. And then the last factor of 10 brings us to 0.0034. So these two numbers, one is expressed in expanded standard notation, and the other is expressed in scientific notation. Now, as you get faster with scientific notation, you're basically going to be operating off of this moving the decimal point way of viewing it. So we're going to get used to that as we do these examples. Okay, first major example is going to be, and this is right off of a problem set I had in college, we're going to write out 5.8 times 10 to the negative 9th meters in standard or expanded form, as opposed to currently it's in scientific notation. So now we look here and we have the instruction of 10 to the negative 9th. Now every time we have one negative power of 10, that's an instruction to move the decimal place to the left once. So just looking back at the example here, we had 3.4 times 10 to the negative third, and what we did is we slid the decimal point once, twice, 3 times to get the answer. So here, all we're going to do is slide the decimal point to the left 9 times. So we start with 5.8, and we're going to slide it once, twice, 3 times, 4 times, 5, 6, 7, 8, 9. Oop, I actually ran out of space. So here's the decimal point, and we have all these zeros in front. Now let's just check that we've done it appropriately. We've gone 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 8 zeros here. And just a side note, that's 8 and not 9 zeros because the first factor of 10 was consumed moving the decimal point past the 5. So there were 8 zeros that appeared in addition to that first factor of 10 that was eaten up. Excellent. So this would be the number written in standard form. Let's do a second example of converting a number to standard form. Let's do 7.8 times 10 to the positive 9th this time in standard form. Okay, now again this time each factor of 10 is going to move the decimal place to the right once. So we're going to move the decimal place to the right 9 times. So 1, that gets it past the 8, 2, 3, 4, 5, 6, 7, 8. Oops, sorry, 9. Now again, we might not have 9 zeros here. It took 1 to get past the 8. If there were another digit there, let's say 7.84, it would take another factor of 10 to move the decimal place past that. But we just checked that we've moved the decimal place 9 times to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9. Perfect. So 7, 8 followed by 8 zeros is going to be the expanded form of that number. Okay, now let's do a little bit of a tricky example. This is something you might see if you do anything involving optics or maybe studying the sizes of cells or atoms. So nanometers is very common. In the next lesson where I cover the metric system and the units, I'll talk about nanometers in a little more detail. But let's write out the number 5.7 times 10 to the negative 7th meters. The goal is to figure out how many nanometers, which is 10 to the negative 9th meters, is this. So our goal is going to be to cache in decimal place or do the opposite, moving the decimal place and eating up factors of 10 until we have a number times 10 to the negative 9th. Now, currently we have 10 to the negative 7th, and our goal is to have 10 to the negative 9th. So what we're going to want to do is every time we move the decimal place to the right, we eat a factor of 10, which corresponds to lowering the exponent by 1. So basically, we're going to be able to, instead of having, let's say, 5.7 times 10 to the negative 7th, we could eat a factor of 10 here to get 57, but but in doing so, we eat a factor of 10, decreasing the exponent by 1. Now we're going to do it again. We're going to move the decimal place to the right and eat a factor of 10. And now we finally have it written as a number times 10 to the negative 9th nanometers. So this is 570 increments of 10 to the negative 9th. So sorry, this is that many meters, and then each 10 to the negative 9th meter is 1 nanometer. So 570 nanometers is the answer here. Now I'm going to write, this is going to be classified as a challenge example because it is a little harder. It isn't as simple as consuming everything. You have to sort of play with it, and in fact you even take it in the quote-unquote wrong direction. You're adding more complexity to the factors of 10. But you will see this and you will be asked about it often, so it's useful to know. If you feel uncomfortable with this, don't worry about it too much. Come back at the end, go through it slower. With experience, it'll become a little easier to do. Okay, now just like the review at the beginning of this lesson, you're going to very frequently be asked to multiply or divide, and then sometimes add or subtract numbers in scientific notation. Over the course of your problems, and in fact in the next video on the metric system, you're going to see a ton of factors of 10 upstairs and downstairs with positive and negative exponents, so it's going to be really useful to get some practice in with this. So just as a review from the previous part of the lesson, if we have something such as 10 to the 6th over 10 to the 4th, the rule is you can subtract the exponents to get the answer. So this is just going to be 10 to the 2 from subtracting 4 from 6. Basically, the 4 factors of 10 kill off 4 of the 6 upstairs factors. If you multiply 2 factors of 10 together, you just add the exponents, right? This was 5 instances of 10, and this was 2. So altogether, there's 7 multiplications of 10. And last but not least, if you have if you have 10 to a negative power, such as 10 to the negative third, this is actually the same as 1 over 10 cubed, and you can write it like that. Something I perhaps didn't mention before, if you have 1 over if you have 1 over 10 to the negative third, you can bring the 10 upstairs at the cost of the exponent. So bringing things either above or below the fraction sign eats the negative in the exponent. And the reason that this works is, remember, 10 to the negative third is 1 over 10 cubed, and 1 over a number, so in this case that number is 10 third, is just that number again. So that's why this works. All right, so now we're going to look at some examples of multiplying numbers in scientific notation. Again, you will do this a lot, so it's really good to get a bunch of practice, make it become automatic before you get into problems with it, and then by that time when you're actually doing problems, you'll know exactly how to do it without even thinking twice. All right, so first we'll start off with example A. We're going to do 3 times 10 to the 5th times 6 times 10 to the 8th. Now remember, whenever you're multiplying a string of numbers together, it doesn't really matter which order you multiply them in. So in this case, we're free to rewrite this as 3 times 6 times 10 to the 5th times 10 to the 8th. And we can basically simplify things in chunks however we want to. So the first chunk, 3 times 6, just simplifies to 18. And the second chunk, we see we have 2 factors of 10 with exponents being multiplied together. So whenever you have exponentials being multiplied of the same base, you just add the exponents. So in this case, we're going to add 8 and 5 together to get 10 to the 13th upstairs. So this is pretty close to our answer. It is a correct number, but if you want to write it in scientific notation, the correct prescription is to have only one number before the decimal. So we currently have the decimal point here, and we want to move it over to there instead, and store that factor of 10 inside of the exponent. So instead of 18 times 10 cubed, again, we're going to move the decimal place over to the left one and increase the exponent by 1. In response, in reverse, you could consume the factor of 10 we just stored in here to bring 1.8 back to 18. So the answer would be 1.8 times 10 to the 14th, written in standard form. Excellent. Now let's do another example, this time involving a negative exponent. We're going to do 3 times 10 to the 7th times 4 times 10 to the negative 5th. Now, same thing as before. We're able to mix and match these numbers as we want, write them in any order. All right, on the right we have 10 to the 7th times 10 to the negative 5th. Now remember, whenever you're multiplying two factors of 10 together, you can just add their exponents. So this will simplify down to 10 squared, and this part is 12. Now, if you wanted to, you could write this as 12 times 100 is 1200, but if your teacher asks for it in scientific notation, your command is to move the decimal point over to the left until there's only one number in front of it. So in this case, we're going to move it to the left and store that factor of 10 in the exponent like before. So 1.2, and then we ratchet up the exponent by 1 to get 1.2 times 10 to the third. Again, it might be more clear if you go in reverse. You can eat up the factor of 10 we just stored in 10 cubed to convert 1.2 back to 12. That's like a check to make sure that you did it in the right direction. And I find myself doing that check very often. In fact, you'll notice I was a little slow on one of these examples up here, because I was really checking that I did it right. There's no harm in repeated checking of this stuff because it's easy to make mistakes. All right, example C, we're going to do a division this time. 6 times 10 to the 7th divided by 2 times 10 to the negative 8th. Okay, there's a division and there is a negative exponent. Now, of course, there's a few ways you can simplify this. You can bring the 8 upstairs first. You can do subtraction of the exponents. Either way will work. Like before, we're able to break stuff up because it's just multiplication and division, and we can simplify parts as we want. So the 6 over 2 obviously gives us a 3. Now, the second part with the tens, one of you might choose to first bring the 8 upstairs, which is something that I like to do. So instead, we have 10 to the 7th times 10 to the 8th, and now we know that you can add the numbers and get 3 times 10 to the 15th as your answer. Other people might choose a different way, which is totally fine, and it's to leave it as a division and do 7 minus the downstairs exponent, which is negative 8. So 7 minus negative 8 is 7 plus 8, which again is 10 to the 15th. So each way works, and it's whatever you find more visually intuitive. All right, and lastly, let's do a combo example here. We're going to do 8 times 10 to the 8th divided by, and two things in the denominator, 1 times 10 to the 10th, and also in the denominator, 2 times 10 to the negative third. So as usual, we're just going to handle all the factors of 10 and then see what happens to the other numbers after. So the 8 over 2 will leave us with a 4. So that handles these guys. Now let's see what factor of 10 we have left after all these guys cancel. So again, there's multiple routes here. I'm going to take the route of doing upstairs exponent minus any downstairs exponents. So we have 10 to the 8 minus 10. And then, again, since negative 3 is appearing downstairs, we're going to subtract off whatever exponents appear downstairs. Right? We're not doing 8 minus 3. We're doing the upstairs exponent 8 minus whatever exponent is appearing currently downstairs, which is still negative 3. And this gives us 4 times 10 to the, let's see, this is negative 2 plus 3. Which is 10 to the first. So 4 times 10, and if you want, you can write 10 to the first power. So 40, or 4 times 10 to the first, is the answer here. Now again, if you wanted to, you could bring the 3 upstairs, and in that case, you'd have 8 and 3 upstairs for 11, and then 10 downstairs. So you'd subtract, when you were simplifying, you'd do 11 minus 10 from downstairs gives you 1 left over. So both ways will give you the same answer. Okay, we're going to do one final example, then I'll do some closing comments on how you can punch these in on your calculator. and then we'll wrap up the lesson there. Okay, this is also going to be sort of a challenging example, but it is important to know how to do. It's how do you add numbers in scientific notation? So 3 times 10 to the negative 2 plus, now this is not multiplication, it's a plus sign. And this tends to be more difficult because you can't randomly add parts of these like you could multiply things together. Okay, now the rule is, or I guess the general strategy is, you want to write these numbers so that they both have the same 10 factor appearing. And then what we're going to do is we're going to pull the 10 factor out from both of them once we have it there. That's going to be the factoring thing that we did before that I covered at the beginning of the lesson with the distributive property. So the goal is going to be massage this until it's in the form number times 10 to the negative 2, and then we will be able to factor out, pull off the 10 to the negative 2 from both terms. So what we can do is we can cash in moving the decimal place over by 1. So we started with 4, but we're going to move it over and get 40. And in exchange, we lower this by 1. And again, I'm just going to check that I did this right. I need to make sure. If I wanted to, I could use one of these divisions by 10 to convert the 40 back to a 4. So I know I've done it in the right direction. Okay, so now I've gotten my goal here. I have 10 to the negative 2 on top of both, and I'm going to yank it off and put the rest of the stuff in parentheses. Now I'm able to add these numbers because they're not attached to factors of 10 anymore. It's been isolated outside. And now if I want to express this in standard notation, I can move the decimal place over to the left one at the cost of increasing this exponent by 1. Now let's just check that I did this right. I used one of these divisions by 10, so there's only one left over afterwards, to move the 43 and convert it to only being 4.3. So yes, I did do that in the right order, and that's the answer. Now again, this is much less common. You won't see it in problems very often, and when you do, you'll often be able to use your calculator. However, it's very useful to know how to do in general. And also if your tests are no calculator. Okay, so that's the end of the actual lesson. Now there is a really important comment I want to make about how you punch these into your calculator. So important, I'm going to write it in this cool Galaxy pen. So how to enter into calculator. Now this is really important because it is conceivable that you could do everything right in the problem and forget to put a parentheses on your calculator, and it will spit out the wrong answer. And you will never be able to figure out where you went wrong. And really, you didn't. It was just punching it into the calculator that went wrong. So the calculator will understand everything is being multiplied unless you group it into when you divide by something on your calculator. So for example, if you're doing 3 divided by, let's say you're asked to punch this in your calculator. If in your calculator you enter 3 divided by 4 times 10 to the negative 5th, it will interpret this without these parentheses around the outside like you want. Instead, it's going to think you want to do 3 divided by 4 times 10 to the negative 5th, when really you want to be dividing by 10 to the negative 5th. So what you have to do is be really careful to put these in parentheses. Okay? You're going to want to make extra sure of that because it's really easy to forget about the parentheses. In fact, when dealing with scientific notation, I will often do 3 divided by, I'll input both parentheses, because I don't want to forget, and then I'll move the cursor over, and then I'll write in my number. Another comment is calculators often have a shortcut key for scientific notation. And it's called the E, or sometimes the EE key. This is not to be confused with the lowercase e key that is some random number that appears in physics that's 2.7, some constant like pi. This will allow you to write things like 4, and then you hit the E key, -5, and this is the same thing as 4 times 10 to the -5th. It'll automatically group the -5 up there. Now, if you use this notation, on most calculators you can get away with dividing by it without parentheses. I'm pretty sure on most calculators you're able to, but if you're writing it out like this, you need to be extremely careful when putting it into your calculator that you don't accidentally forget the parentheses. Okay, final thing, just a quick note. Some people often get really concerned about significant figures, especially if you've taken chemistry. Thankfully, in physics, you don't have to really be concerned about significant figures that often. What I would recommend is keep about 4 numbers in your scientific notation. For example, if you have a number that's this, you don't need to write it as 2.943782 times 10 to the, what would this be, 1, 2, 3, 4, 5, 6, 7. You don't need to keep all these extra digits. It kind of defeats the purpose of scientific notation. So in general, I would leave this as 2.943 times 10 to the 7th. And I would forget about these guys because unless you need an answer to be accurate to 5 non-zero numbers, so for example, if your answer cares about whether you're writing 2943780 or 2943780, which almost never happens, you don't need to worry about keeping too many of those decimal places. So as a rule of thumb, if you keep 4 numbers in your scientific notation, it's fine if some of them are 0. You should have enough rounding that any program, even like web-assigned programs, shouldn't care too much about. If you want to be really safe, you could add 1 more number in, but you don't need to be too careful about it. Alright guys, that about wraps up today's lesson. If you have any questions, please leave them below. I'm going to be updating these videos as questions come in. And once again, if you found this helpful, the best thing you could do to help us out would be to spread this around in your class. Hopefully other people could benefit from it too, and at the same time help the channel grow. We appreciate it. Alright guys, have a good one. I'll see you next time.